Today, we're not just going to solve an electrostatics test, we're going to decode it. The goal here is to break down every single question and really show you the core strategies that you can use to solve any problem like it. So yeah, let's get right into it.
All right, first things first, we need a little shift in perspective. A physics test isn't some big scary obstacle, right? It's really just a series of puzzles, and each one has a logical, kind of elegant solution waiting to be found. And today, we're going to piece those solutions together, one clever step at a time.
So our first puzzle is all about those invisible forces that pretty much shape our universe, electric fields. We're going to explore how to map them out, how to calculate their strength, and predict exactly how they're going to behave.
Before we jump into any of the math, let's make sure we absolutely nail this core concept. An electric field, it's like a cheat sheet that a charge creates all around it in space. It basically tells any other charge that wanders by, hey, here's how much force you're going to feel, and here's the direction you're going to get pushed. You know, really getting this idea is the key to, well, everything that comes next.
Let's ease into it with a classic one-dimensional problem from the test. This is question 7. So we've got two charges sitting on a line, and we need to find that one sweet spot where their electric fields totally cancel each other out. You can think of it like a tug of war, where these invisible fields are the ropes just pulling and pushing on a single point in space.
Okay, so since that first charge is positive, its field points away from it, which at the origin means it's pointing to the right. Now, to cancel that out, the second charge, Q, has to create an equally strong field pointing in the exact opposite direction, to the left. And that one little observation tells us something huge. Q must also be a positive charge, pushing away from itself. The two fields have to be in perfect, balanced opposition.
All right, now let's crank up the difficulty a bit and move to a 2D problem, question 9. At first glance, this thing looks like a total mess, right? 4 charges all pushing on that center point P. But listen, the key here isn't to start calculating like crazy. It's about spotting the symmetry. Seriously, before you ever write a single equation, always look for what cancels out.
Just watch this. The field from the bottom left charge points up and to the right. The field from the bottom right charge, it points up and to the left. See it? Their horizontal parts cancel each other out perfectly. Gone. We can do the same thing if we think of that plus 2q charge as just two separate plus q charges sitting together. The field from the top left plus q cancels with the field from one of those plus q's at the top right. And just like that, this problem that looked super complex, something that could have been a whole page of vector math, it just simplifies down to finding the field from a single plus q charge. That right there is the power of symmetry.
So we've just seen how competing fields can cancel out. And you know what? That exact same principle of cancellation applies to forces. So let's dive into what happens when all the forces on an object cancel each other out, creating this state of perfect balance that we call equilibrium.
For these types of problems, there is a universal method, a 4-step toolkit that will guide you every single time. First, you isolate your object. Second, draw every single force acting on it. We call that a free body diagram. Third, you take any of those diagonal forces and you resolve them into their simple up, down, and left-right components. And finally, you just balance the forces. Everything going up has to equal everything going down, and everything going left has to equal everything going right.
Let's actually apply this to question 5. Here, we've got two charges hanging from strings. So gravity is pulling them straight down, the tension in the string is pulling them up and inward. And because they have the same charge, the electric force is just relentlessly pushing them apart. At equilibrium, all of these pushes and pulls just lock into this perfect, motionless balance. And guess what? The same toolkit totally cracks question 8. In this one, a single charged object is hanging in an external electric field. Gravity is pulling it down, the string's tension is pulling it up and to the left, and the electric field is shoving it to the right. It's a three-way tug-of-war, completely frozen in time. And by breaking that angled tension force into its components, we can set up our simple balance equations and solve for pretty much anything.
Okay, so far everything has been perfectly static, perfectly balanced. But let's be honest, the really exciting physics happens when we push things out of balance, when charges actually start to move. Let's explore some of the more dynamic problems from the test.
This is the question, right? This is what takes us from the world of statics into dynamics. An unbalanced force means acceleration, and acceleration means motion. And when you're talking about charges held in a delicate balance, this can lead to a really fascinating rhythmic thing called oscillation. Let's set the stage for question 10. Imagine this. We've got two positive charges that are fixed in place. And right in the middle, we put a negative charge.
At that exact center point, the pull from the left charge is perfectly balanced by the pull from the right charge. The net force is 0. The charge is in equilibrium. It's happy there.
But here's where it gets really interesting. If you just nudge that negative charge a little bit to the right, it gets closer to the right-hand charge, which makes that pull stronger. And at the same time, it's farther from the left one, so that pull gets weaker. The result, a net force that yanks it back towards the center. This is what we call a restoring force, and it's the absolute hallmark of simple harmonic motion. The charge has inertia, so it overshoots the center, and then it just gets pulled back from the other side. It will literally oscillate back and forth, back and forth.
And now, for the most abstract puzzle on the test. This is the kind of question that doesn't just ask you to apply a rule, it challenges you to imagine a totally new one. This is a true test of whether you really understand the fundamentals of physics.
So question 3 asks us to imagine a universe where the force between charges doesn't follow our familiar inverse square law. The key here is to go back to the most basic definition there is. The electric field is simply the force experienced per unit of charge. That's it. So if the force law changes, all we have to do is take that new hypothetical force equation and divide it by the test charge, Q, to find the new expression for the electric field. It shows that direct, unbreakable link between the cause, the force law, and the effect, the field.
Whew! Okay, we have worked through a lot of different puzzles, from static fields all the way to oscillating charges. So now, let's just take a step back and review the key strategies we've uncovered. These are the tools you can add to your own mental toolkit for any physics problem you face.
First, and this one is huge, always hunt for symmetry. It can turn a page of boring math into a single beautiful insight. Second, you have to draw the forces in a free body diagram. It makes the physics visual and way more intuitive. Third, remember superposition. You can just figure out the effect of each charge by itself and then add them all up. For anything that moves, find that restoring force. And finally, when a system looks totally overwhelming, just break it down. Isolate and analyze one piece at a time.
So, what's the big takeaway from all this? Behind every complex-looking problem, there's always a set of simple, really powerful ideas. These aren't just some abstract rules you memorize for a test, they are the fundamental tools we use to describe our entire universe. So the real question is, now that you have these tools, what are you going to build with them?